Okay, the recording has started. So good morning, everybody, and welcome back to Math 115. Or I suppose if you're watching the recording, then good afternoon or good night. In any case, we're going to start today's class, and I kind of had thought about teaching one more section, but I decided against it. So what we're going to do instead is this week, and also I think we have like one class on Monday next week, maybe. We're going to review for the final exam. Okay, so it's time to review for the final exam, which means that our class is going to sort of take the following format for the rest of the semester. We will do, I have a big bank of previous final exams that have been given by other instructors with some interesting problems on them. So I will bring one of those to every class, and we will take a look at that exam and some of the questions on it. Most of them have material from, all sorts of trigonometry, exponentials, logarithms, polynomials, graphing, and all sorts of stuff that we've done. So what I'd kind of like for the students of the class to do would be to come to class prepared with an idea of maybe one thing that you want to review, or if you're doing some review on your own, which is great, and you come across something that's confusing, then please do bring it to class and we'll discuss. So the sort of MO for moving forward will be, will just be that I'll bring those exams and go through those, unless there's something that a student brings to my attention, in which case I will dive into that. So please do make use of it. I'll be here, so you guys are more than welcome to, bring your own personal study problems that you want to learn about and get them talked about during lecture. Okay, so how does that sound to everybody who's here? Sound good? Sound like a plan? Any further suggestions? Okay, sweet. All right. So here's an exam, and I can't believe that somebody actually gave this exam, just because it's really long. It's like 30 questions long. But it's got everything from trig and some word problems and some log equations and some interest, sketching of graphs, simplifying rational expressions, dividing and multiplying rational expressions, inverses, polynomial long division, domain and range, rational functions, parallel and perpendicular lines, distance and midpoint, and a bunch of these true and false. So does anybody want me to start somewhere other than just the beginning and moving through? For example, if you heard me talking about those topics and one of them you went, oh crap, I forgot we even learned how to do that. I could never possibly produce that on the final exam. That would be a good place to start. Okay. Well, I don't want this to totally devolve into me just solving a practice exam for you guys. So I'll try to involve you guys a little bit. So let's just start with these true and false questions, and we can think about these together. So the first one looks like, okay, we've got 2y plus 5 divided by 2y is reduces to, I think that should have been a y here. Reduces to y plus 5 over y. Okay, so it looks like moving from left to right, what have we done? We started with 2y plus 5 over 2y, and now we have y plus 5 over y. So it looks like we've sort of canceled these 2's here have been canceled. So what do we think? True or false for this? Is this a way that we can reduce this rational expression? Okay, Morgan says false. Anyone agree, disagree with Morgan? All right. This one is false for sure. Definitely false. And maybe I can comment on the reason why. The reason why this is false is because essentially, if you want to cancel a common factor from the numerator and the denominator, okay, it needs to be present in both of the two terms which are in the numerator and all of the terms which are in the denominator as well. So we've got a 2 as a factor in the denominator, but 2 is not strictly speaking a factor of the numerator, because while 2 can evenly come out of 2y, it can't actually come out of 5. So the reason that these two things are not equal, I mean, you can just put them next to one another and use principles of algebra to check if they're equal. I mean, if you want to check, is this equal to y plus 5 over y? You know, you just multiply both sides by y and then 2y, so you get y times 2y plus 5 is equal to 2y times y plus 5. Right? And then you get 2y squared plus 5y is equal to 2y squared plus 10y. Right? And you subtract 2y squared, so these guys would go away. You divide both sides by y, and you'd get 5 is equal to 10, which is definitely not true. Okay, so the problem is that the 2 here was not present in the 5. Okay, if we want to take a 2 out, then we would have to do like 2 times y plus 5 over 2 or something like that. Then you could maybe take a 2 out and cancel if you wanted, but then you'd have another fraction in the numerator. So this is not a way that we can reduce a rational expression. Okay, number 2, we've got another rational expression, equivalence here. We want to check if -3 divided by a minus 5 is the same thing as 3 over 5 minus a. -3 over a minus 5, is it the same as 3 over 5 minus a? What do we think? True or false for number 2? We have some ideas about number 2 here. Maybe what seems like it could have happened to go from one direction to the other direction? What process might have sent us in this kind of direction? Two falses coming into the chat so far. Does everyone agree that this statement number 2 is false? Or are there any truthers out there? So far, everyone agrees on false. I'm going to disagree. I think this one is actually true. And to see why, I'll say that we can multiply the numerator and the denominator by a certain number. What number can I multiply the numerator by to go from -3 to 3? I want to take -3, multiply by -1. There we go. -1 to get 3. And then if I multiply the denominator by -1, well, a minus 5, if I multiply that times -1, then I get -a plus 5. And I can do addition and subtraction in any order that I want. So I can rewrite this as 5 minus a. So this one's actually true. And to see it, you could maybe do this process again where you set them equal and multiply things out and see what you get. And you'll see that it's actually true. So that's a tricky one there. They kind of just multiply the numerator and denominator by -1. Okay, it's kind of like how -3/2 would be the same as 3 over -2, right? Whether we divide by a negative number or multiply by the negative number doesn't really matter. It's just tricky because of the binomial expression in the denominator. I think it looks very different, a minus 5 versus 5 minus a, but those are actually the negative of one another. Okay, so that's a tricky one. That one's true. All right, now we've got two functions here. F of x is equal to 5x, and then g of x is equal to x over 5. Then f composed with g of x is equal to g composed with f of x is equal to x. Wow, that seems like a pretty strong claim. Well, we can check it. We've got f of x is equal to 5x and g of x is equal to x over 5. So how should I do f composed with g of x? Well, we know that f composed with g of x, it's been a while since we've seen this notation, okay? But we can kind of think of this little o here as meaning of. Okay, so when we see f composed with g of x, okay, we can think of this as being f of g of x. So how do I plug g of x into f of x? How do I take two functions and plug them into one another? Well, what I want to do is I want to take all of g of x, which is x over 5, and I want to plug that in for x in f of x, right? This is how we do this composition stuff. So f of x is 5x, but instead of writing x, I'm going to then plug in the function g, which was x over 5. If we do 5 times x over 5, we get x. So it's true in this direction, at least. But we're also supposed to check whether the same thing is true of g composed with f. So if we want to do g composed with f, remember this little circle here kind of means of. So we can write g of f of x. And then now we just want to take f of x and plug it in for x in g. Okay, so what I'm going to do is I'm going to take this whole 5x here, and I'm going to plug that in for this x, which is in G. Okay, so I'm going to plug it in. So I would get, well, G is x over 5, but I'm going to use f of x instead. So this is equal to f of x over 5. And f of x is 5x. So we do 5x over 5, and we get x. So if I do f composed with g, I get x. If I do g composed with f, I get x. So we verified that this is true. And my question for you guys is, what relationship then holds between f and g? We have some special terminology for the relationship between f and g. When this relationship is true, we say that there's a special word we use for the relationship between the functions f and g. Anyone remember what that word is? Well, I may be able to jog your memory by drawing the following diagram. If we have our conveyor belt system, we start with the number x, and it goes into the f function, then out pops 5x, and then 5x goes straight into g, and then out pops x. So we started with x, and we end with x. That's right. We're going for the inverse function here. These two functions are inverses of one another. G of x is exactly f inverse of x in this case. Okay, this is the definition, really, of inverse functions. Is f composed with g is equal to g composed with f is equal to the identity, right? They undo one another. The f function takes whatever number you had and multiplies it by 5. And the g function takes whatever number you had and divides it by 5. And those are sort of the opposite process, right? So these functions are inverses. All right. Next one. Any set of ordered pairs is a function. Well, what do we think about this one? Any set of ordered pairs is a function. Okay, so we're talking about a set here, so let's remember what that means. A set is something like, a bucket, and inside our bucket we have our items, and in this case the items which are in our bucket are ordered pairs. So we have things like, 1, 3, comma, 2, 4, comma, dot, 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 some other stuff. And the claim is that just any old set of ordered pairs is going to be a function. Okay, what do we think about that claim? Any set of ordered pairs is a function. Well, the question seems to be asking something about, I think really the key word of this problem is function, right? And at the beginning of this class, we had a sort of a specific definition of a function. And for something to be a function, it had to satisfy certain criterion. Does anybody remember what that criterion was? That can provide that information for the class. Sure, vertical line test. That's one way to think about it. Right, if we want it to be a function, it should definitely pass the vertical line test. Okay, so if I have a set of ordered pairs, right? You know, I wish I could like add space in between these things. Maybe I will. I'll add a page and I'll go into here. Yeah, vertical line test is good. So if I have a set of ordered pairs, just any old set of ordered pairs, what does it look like on the coordinate plane? It just means, well, I have some collection of like, my points, which I said, I don't know, I copy this down. I have some collection of ordered pairs. And what do they look like? Well, if I want to graph them, I just take each ordered pair, like the ordered pair 1, 3, that goes here. The ordered pair 2, 4 goes somewhere up here. And then I have like a whole bunch of other points, just like off in the middle of space, going all over every which way. And I don't actually have an idea of what the ordered pairs are, which are in the set. But the claim says that no matter which ordered pairs are in the set, it's going to be a function. So the question is, could I possibly have a set of ordered pairs such that when I graph it on the coordinate plane, two of my ordered pairs are going to be in a vertical line like this, such that the vertical line test is failed, right? What do we think? Can I include such things? The wording was any set, right, of ordered pairs. So in particular, in mathematics, if you want to be able to say that this is a false statement, we're just going to need to come up with one set of ordered pairs, which is not a function. Because the claim is quite strong. It says every set of ordered pairs is a function. So I would posit false. And if I were asked to give a reason, which of course I always ask for reasoning on the true and false questions. If I were to give a reason, the reason would be, well, the set of ordered pairs 0, 1, comma 0, 2 is not a function. And I would say something like, well, it has repeated x values. Or fails vertical line test. Right? 0, 1, and 0, 2, if I were to graph it, we'd have 2 points. The first point would be at 0, 1, and the second point would be at 0, 2, and these 2 points don't form a function because we have repeated x values going to different y values. Okay, so that was about functions. Okay. Next up, number 5, we've got the function f of x equals e to the x. The claim is that this function has a horizontal asymptote at the x-axis. So let's think of f of x equals e to the x. Well, what does it look like? Well, first of all, we have two axes here. The x-axis is the one that goes left and right, right? And then the y-axis is the one that goes up and down. So the claim here is that the function e to the x has a horizontal asymptote at the x-axis. which means it gets closer and closer and closer. To this horizontal line, which is the x-axis. Okay, this horizontal line, which is the x-axis. So if I draw the function of f of x equals e to the x, okay, I want to check, well, is it somehow getting closer and closer to the x-axis in some way? Well, if we remember what the graph of e to the x looks like, we know that anything to the power 0 would be 1. So we know that e to the x goes through the point 0, 1. Right? And then if we take some number, which remember e is something like 2.7 something, 2.7 something, and if we make the power larger and larger and larger, right, then this function's like getting really, really big. It's kind of blowing up, right? But in the other direction, when x is becoming negative, we have e to the negative 1 is like 1 over 2.7. E to the negative 2 is like 1 over 2.7. I should have put approximately 1 over 2.7 squared, right? E to the negative 5 is something like 1 over 2.7 to the 5th power. And I claim that this number is getting very, very close to 0, right? Because I divide by 1 by a huge number. If I divide 1 by a really big number, something like 1 over 1 million or 1 over 1 trillion, right, is really close to 0. So what's happening on the left-hand side? Well, we see that this line, this curve, will be getting very, 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 very close to the x-axis, but never touching. Getting very, very close but never touching is really sort of the definition of an asymptote, isn't it? So I think this one's definitely true. Okay. The other way to see this is e to the x has a horizontal asymptote at the x-axis. The x-axis is defined by the equation y equals 0. So in other words, there is some sequence of x values such that the height of the function becomes arbitrarily close to 0. And yes, there certainly is. It's the sequence of x values which go to the left. Okay, so that is just reminding us what is the definition of an asymptote. Okay, so next up we've got the graph of y is equal to 2x plus pi over 6. Sine of 2x plus pi over 6. And the claim is that this function has period pi and phase shift pi over 6. So two things have to be true in order for this statement to be true. It has to have period pi and phase shift pi over 6. Well, what do we think about the second part? Phase shift pi over 6. Do we agree that this function has a phase shift of pi over 6? You know, this is not the final exam, so this is really the safest place to be potentially wrong. So don't worry about putting something wrong in the chat. Okay, this is like totally safe space. No points are being given out today. So I think voluntary participation is really kind of in your own best interest. Agreement coming in for phase shift pi over 6. I think that's good because phase shift, remember, just means horizontal shift. We have a horizontal shift if we add or subtract something inside the parentheses. And we can see we are adding something inside the parentheses, and it's exactly pi over 6, which is what it says the phase shift should be. So I think this part is plausible. So that part's good. And now we just need to check whether it has period pi. Well, we know the original sine function has period 2 pi. sine of x has period pi, 2 pi. What do we think about sine of 2x plus pi over 6? Well, the plus pi over 6 is not really going to affect our period. So we just need to consider the only other transformation that we have, which is 2 times x in here. What kind of transformation is this? What happens if we multiply the input by 2? What kind of transformation is that going to give to us? If we take our input here and multiply by 2. Already got the horizontal shift taken care of. So if we multiply by a number on the inside of the parentheses, what does that one do? We're on the right track with stretch, but I think it's going to be not a vertical stretch, but a horizontal stretch or compression. Right? And whether it's a stretch or compression depends on whether our number here is larger than or smaller than 1. Okay? So here's a quick reason why this is going to be a vertical stretch and not a horizontal stretch or compression and not a vertical one. A vertical stretch is when we multiply by a times f of x. Then what happens with the graph is we do y is equal to a times f of x, and we just take, the height of f of x, and we just take that height and multiply it by a to then get a times f of x. Okay. However, if we have something like, so this was in green. If we have something instead, such as y equals a f of a times x, then this is going to give us a horizontal compression for the following reason. Okay, what I do is I go to an x value. Okay, and then if I want to find the height of the function f of a times x at this point, what I need to do is take my x value, multiply by a, which means go over to ax, find the height of the function f of x, f of ax, and then that gets kind of moved over to be the height of my function y equals f of ax. Okay, so this is why multiplying on the inside is going to give us this kind of left and right compression or stretch, and then multiplying on the outside is just going to give us a straight up and down kind of stretch. Okay, and from this example, it's clear also that ax will be to the right of x as long as a is bigger than 1, and ax will be to the left of x if a is less than 1. Right? So if a is larger than 1, things that are to the right are getting kind of moved backward towards the y-axis. So if a is larger than 1, we get a horizontal compression. And if a is less than 1, we get a horizontal stretch. Because things that were previously here get mapped a little bit to the right. Okay, so that's the short version of why this happens. But in any case, if we were on an exam, of course, we would be able to go back to our notes and check what multiplying by a number on the inside does. And if we did that, we would find that 2 is larger than 1. Therefore, we get a horizontal compression by a factor of 2. If you want to see what that looks like, I'll show you in Desmos. We start, of course, with just the regular sine function. So let's do just sine of x. And then the next function, I'm going to forget about the phase shift for a second, just to show you what this transformation does. We do 2x instead. Basically, it just wiggles a lot more. Okay, and since we've compressed this whole graph, we've scrunched it by a factor of 2. What is going to happen then to the period? Remember, the period is the distance from crest to crest. So if I compress by a, oops, that's the wrong app. If I compress by a factor of 2, what does this do to the period? Is our period going to be shorter or longer than it was before? What happens to the period of a trigonometric function under a horizontal compression? Good, it's going to be shorter, right? What happens to the period is the period is compressed commensurately, meaning by the same factor. So our new period is going to be 2 pi, our old period, divided by 2. So our new period is pi. And this is exactly what the question was asking. The question said the graph of sine of 2x plus pi over 6 has period pi and phase shift pi over 6. We already verified that there is a phase shift at pi over 6. And we just checked that this horizontal compression, right, is going to compress the period of our graph by 2. The period of sine x was 2 pi, so if we compress it by 2, the new period will be half of what it was before, and therefore the period will be pi. So this one's going to be true. Okay, so another true. All right. Any questions on this, I guess any of these true and false questions? How do we feel about them? Do we feel good or feel like, man, that was kind of hard? Starting to remember this. Yeah, see we've been doing trig for so long that I think that a lot of this stuff from the start of the semester has kind of started to fade, which is why I wanted to take these extra days to do more review. I think it'll be good for everybody. Am I going to upload this as the notes for the week? Yes, I will. Yeah, in fact, maybe it would be good. I'll put a couple of practice exams on the blackboard, and I'll tell you which ones I'm going to go through on which days. And that way you can try them on your own if you want before coming to class. That might be helpful. Okay, cool. I think these true and false questions, are, not unlike the ones that we have on our exams, where, they're true and false, yes, but seeing whether they are true or false involves a decent amount of checking. Especially this last one, number 6, we had to check quite a bit, right? Or number 3, we had to do a little bit of computation to check whether that's true. It wasn't immediately obvious. So anytime we have a true and false section like this, what we should do first is justify whether we believe it's true or false before we write whether it's true or false. Because just looking at it is usually not enough to tell whether it's just going to be true or false off the bat. We got to check. All right. So next question, we're going to do some graphing. We're supposed to find the equation of the line which is parallel to the line 2x plus 3y is equal to 4. Okay, 2x plus 3y is equal to 4, and it should contain the point -3, 0. Okay. Now let me ask you guys if you can remember what it means for two lines to be parallel. What does it mean for two lines to be parallel? What happens if two lines are parallel? You have two parallel lines, and something should be true about them. What is that? Yeah, that's two great characterizations. The first one is they never intersect. Yeah, that's definitely a good way of thinking about it. Or you could say they have the same slope. Now, I think that for figuring out the equation of a new line, which is going to be parallel to this one, I think the second characterization is going to be of more use to us. So we're going to take a look at the slope of this line. Okay, the slope of this line, and then we're going to check. We're going to build a line which goes through the point -3, 0, and has that slope. Okay, so first of all, let's call this line 1. And there's one thing that is a little bit confusing about this problem, which is that they give us the equation of line 1 in, quote, standard form. And it's not immediately clear what the slope of this line is, but it will be clear if we get it into slope-intercept form. So I think the first thing we can do is take 2x plus 3y is equal to 4. We're going to subtract 2x from both sides. We get 3y equals -2x plus 4. And then I'm going to divide both sides by 3 to get y is equal to -2/3 x plus 4. And now line 1 is in slope-intercept form. This is line 1 in slope-intercept form. Now we have two pieces of information. We want to build line 2. What? No. Line 2 should have first thing that line 2 should satisfy is that the slope of line 2 is the same as line 1, i.e. m is equal to negative 2/3. The second thing that line 2 should satisfy is that it passes through the point -3, 0. Now, how can I make the equation of a line which satisfies these two things? We have a condition on the slope of the line, and we have a condition on a point which the line passes through. How can I then build the line? How can I build the line if I have a slope and a point? How can I get the equation of line 2? Definitely. We could use the slope and plug in for x and y. So we know that this thing should have y equals mx plus b, right? And we even know that m should be negative 2/3, so we'd get y is equal to negative 2/3 x plus b. And we know that this is a point, so this is the x and y value, which will satisfy this equation. So we plug it in. So I plug in -3, I get, and 0 for y, I get 0 is equal to negative 2/3 times -3 plus b. And therefore, if I multiply that, I'd get negative 2/3 times -3 would be just 2. And I'd subtract it over to the other side, and I get b is equal to -2. And therefore, y is equal to negative 2/3 x minus 2. Or there's another way I could do this. I could use point slope form, right? I have a point and I have a slope. I can use point slope. Point slope is y minus y naught is equal to m times x minus x naught. So I would just plug in x naught and y naught would be these two. This would be my x naught, and then my y naught would be 0. And I'd plug those in, and then I'd also plug in my slope negative 2/3. Right? So you can use point slope, or you can use the sort of plug in and check for b method. Either will work. It just depends on which one you like better. If you memorize point slope might be a little bit faster. But the other hand, the other method that we did originally sort of has the advantage that you only have to remember one equation and a process. And so that's sort of less to memorize. Okay. Any questions about the parallel problem? Next time we will try a perpendicular line. And then continue with this practice exam. So I'll post this onto the Blackboard so you guys can check it and maybe try some of these problems on your own. And other than that, office hours start now and go until 10:30. So if you want to hang out and ask more questions or learn more things, then feel free. Otherwise, I think we're done for today, and I'll see you guys all tomorrow. Yep, thanks, Heidi, you too. Morgan, you want to talk about some stuff?
Yes, like can we practice like literally anything, but like I have a really hard time with like getting stuff in like slope intercept form and like finding slope and stuff.
Sure. Let me add a page up here and we'll work on some stuff. And also let me put my headphones on. All right. So for lines and slope and this sort of thing, I guess maybe we can just start back at the beginning of what is a line. Well, a line is a collection of points which satisfy a linear equation. Okay, when I say a linear equation, what I mean is no square terms. I mean no terms with powers or trig or x's and y's in the denominator. For example, 2x equals y is linear. 2x squared equals y is not linear. X over 2 equals y is linear. 2 over x equals y is not linear. Okay, so we have a linear equation, and the line is just a collection of points which satisfy that equation. Okay?
Okay.
So we have three forms typically seen for linear equations. They have three common forms, three most common forms. We have slope-intercept form. This is y is equal to mx plus b. Here, m and b are real numbers. Okay?
Okay.
For example, y is equal to 3x plus 17. This is an equation of a line in slope-intercept form. Okay?
Okay.
Next form is, I guess, point-slope form. By the way, the reason this is called slope-intercept form is because m is the slope and B is the y-intercept.
Okay.
Okay, we'll talk about graphing this in a sec. So next up we have point slope form. Okay, and point slope form is y minus y naught is equal to m times x minus x naught. Here, m, y naught, and x naught are numbers. For example, y minus 1 is equal to 1/2 times x minus 3. Or plus 3, for that matter. Why don't I make it plus 3? Because if x naught was negative 3, then x minus x naught would be x minus negative 3, and that would make a plus.
Okay.
Okay, and the point here is the point x naught comma y naught. And then the slope is, again, this number m.
Okay.
And then the last one is standard form. In standard form, we have something like ax plus by is equal to c. A, b, and c numbers. Okay?
Okay.
All right, so A, B, and C are numbers. And here's how this stuff works with a graph. The graph of an equation, not necessarily a linear equation, but of course linear equations are equations, so this will apply. The graph of an equation is the plot of all points x comma y such that if we plug them in to the equation, it is true. Okay, so it's the plot of all points x comma y such that if we plug them into the equation, it is true. So, for example, let's take this equation, y equals 3x plus 17. Okay, if I take y equals 3x plus 17, then the point 0, 0 is not on the graph, since if I plug it in, if I plug 0 in for x and 0 in for y, what would I get in my equation? I would get 0 is equal to 3 times 0 plus 17, and that would reduce to 0 is equal to 17, is not true. So this is a point which is not on the graph of the line because it doesn't satisfy the equation.
Okay.
However, the point 0 comma 17 is on the graph, since if I plugged 0 in for the x and 17 in for the y, I would get the equation 17 is equal to 3 times 0 plus 17, and that would get me 17 equals 17, and that's true.
Okay.
Okay, so the reason we call these linear equations is because it turns out that if you make a graph of the coordinate plane, okay, if you graph the coordinate plane, and why don't I'm going to move this down a little bit. If you make a graph of the coordinate plane and you plot every single point, such as 0, 17, that if you plug it into the equation, it's true, right?
Yes.
Then the picture that you get is a line. So it will look like this. So for this one, the slope is 3 and the y-intercept is 17. So I would go up to up to 17.
Yeah.
And I would put a point right there. That's the point 0, 17, which we verified is on the graph. And then the slope will be 3, so it'll look something like this, right?
Okay.
And if I choose any old point on this graph, such as this point right here, if I plug in, if this is x comma y, and I plug it into the equation, it'll be true.
Okay.
So this is about how we find the graph of an equation. There's one thing I still haven't commented on, which is sort of the definition of what the slope means. Okay?
Okay.
So let's talk about what is slope. Parentheses m. It's the m value in all of these equations. Okay, well, slope. Have you ever been on like a road trip through the mountains? And you might have seen a sign somewhere that said like, oh, this is like a 17% grade or something like that. And what it means is the road is really steep, right?
Yeah.
So if you imagine us driving a car on this road here, so here's me in my automobile going up or down, the slope is going to measure how steep the line is. So in this case, it's pretty steep, whereas if a line was more like this, then the slope would be more gradual, right?
Yes.
So we want to use a number to express how steep it is. So we have a couple choices, right? We could try to use an angle if we wanted. That would tell us how steep it is. But what we're going to do instead is we're going to express something in the following way. We're going to say, if I start at a given point and I move over exactly 1 unit, how much higher am I at the end than I was at the beginning? This is how slope works. Okay, so the way we quantify slope is slope is equal to m is equal to rise over run. Okay, rise over run. So for example, y equals 3x plus 17, the one we've been working with so far. Slope, in our case, is equal to m is equal to 3, which is equal to 3 over 1. The way we interpret this move 3 units up for each 1 unit we move to the right. So for example, so this is not necessarily our Cartesian plane, but why don't I just do y equals 3x? So this is the point 0, comma 0, which satisfies the equation, right? Because 0 is equal to 3 times 0. If I move over 1 unit, I should go up by 3 units. Okay. If I move over 2 units, I should go up by, well, I went 2 units, so that's 2 times 1 unit. So I should go up by 3 for the first time and 3 again for the second time. So I go up 1, 2, 3 more units. So then I'm up here.
Okay.
And you can check, by the way, that all of these points here, like I said, satisfy the equation. So this is the point 0, comma 0. This is the point 1, comma 3. And this is the point 2, comma 6. And if I take these and I plug them in to the equation, well, this one's true because 6 is equal to 3 times 2. This one is on the graph of the equation because 3 is equal to 3 times 1. And this one is on the equation because 0 is equal to 3 times 0. Okay, how do you feel so far?
I feel pretty good about it. Still a little hesitant about it, but I feel pretty good overall.
Okay. Then let's talk about this other component here, 17. In fact, why don't I just copy this down? Let's talk about y-intercepts. Okay, so y-intercepts, in this case, I'm talking about this number here. So this is an equation in slope-intercept form. I've got the slope here, 3, which we already talked about, and we also have the y-intercept, 17. Okay, so an equation in slope-intercept form I should say a linear equation. In slope-intercept form passes through the point. So this is y equals mx plus b. Passes through the point 0, comma b. Okay. So why do we call this the y-intercept? Well, if our x-coordinate is 0, then this is going to be a point which satisfies the equation and lies on the y-axis. So this is the x-axis, this is the y-axis. So when we say y-intercept, okay, y-intercept, what we mean is the point which is on the line and is crossing through the y-axis here. Okay, so in our case, for y equals 3x plus 17, it passes through the point 0, comma 17. Okay?
Okay.
And it has slope 3, which means it's going up at a fairly steep angle, I guess. Like this. This is how we could graph this line. Okay? So these are the two components of graphing a linear equation. Are, if we have it in slope-intercept form, we have the slope and we have the y-intercept. The y-intercept tells us, well, maybe I have the slope, right? But the question then becomes, well, which line do you want? Do you want the one that's down here, or do you want the one that's here, or do you want the one that's up here, or do you want the one that's up here? Where does it pass through the y-axis? So if we pin down that it has to go through this one point right there, then that will kind of like complete the unique equation for that line. So the slope tells us how steep should it be, and the y-intercept tells us at which point does it pass through the x-axis. So this is the equation y equals 3x plus 17. But we could also draw the equation y equals 3x minus 6. And that equation would look something more like this. It would have the same exact equation, or same exact slope, right? So it's going in the same direction, except its y-intercept would be -6. So this goes through the point 0, comma, -6. Okay?
Okay.
So this is about y-intercepts. So let's have an example. Let's try to graph y equals -2x minus 3. So I'm going to start with my coordinate plane here. I'll make some markings for us. All right. So we have our y-axis. We have our x-axis. How should I graph this line?
With a slope of -2.
Okay. What else have we got? We've got a slope of -2. What other component do we have?
Sorry, it like kicked me out for some.
No worries.
And then we have a point passing through 0, -3.
Okay. I'm going to draw two points. You tell me which one is 0, -3.
The one on the y-axis.
One on the y-axis, right? So not this second one. So this is the point that it passes through, right?
Yes.
What does it mean that the slope is -2? What's that telling us?
That for every point we go left, it'll be like a decrease, or like, yeah, you go down -2.
Okay, so what I'm hearing from you is we should go to the left, and then left 1, and then down 2. So that would give us a point over here, right?
Yes.
Okay, so this equation looks like this, and our line would look like this. And I think there's a bit of a problem with our line, because our slope is a negative value. Our slope is negative, but we're going up as we move from left to right.
Okay.
So let's review what the slope meant. The slope was the rise over the run, right?
Yes.
So the slope is a fraction. If it's just a number like 3, then it's just 3 over 1. In our case, it's -2 over 1. And the interpretation of the slope is that for each 1 unit we move to the right, we move the numerator number of units up. So if we were to take -2 over 1, which is our slope, then the interpretation of this would be that we move 1 unit to the right. That tells us then to move -2 units up. Well, if I move a negative number of units in the up direction, that's the same as moving 2 units down. Okay.
Okay.
So let's revise our graph here. So -2 means -2 over 1. This is the rise. This is the run. When I say run, what I mean is I move to the right. So where should my next point be? How can I get to it?
Moving to the right one.
So I move to the right one, and then what?
Down 2.
Down 2. There we go. And now this line does the same thing in both directions. So if I want to go to the left, I'm moving to the left, which means I need to think about, well, what is the reverse of what I just did? If I move to the left, I need to go up 2 units, right?
Yes.
Such that for each, phase here, if I move from left to right, I'm going down, right? So this line looks like this.
I know.
Okay.
Okay. Going through these points here.
Now I'm a little concerned about my second dose. Ugh.
Okay, so a negative slope means we go down. So positive slope
Oh, you don't schedule both at once?
is uphill. Negative slope, is downhill, right?
Okay.
And when I say uphill and downhill, I mean as I walk to the right. I'm going downhill in this case, or in the other case, as I move to the right, where did I draw that? I'm going uphill, right?
Yes.
Okay, let's do another one.
So, will we always like move right, or like when is the time that we would move left?
You're also murder now, right?
Well,
You're also
the slope tells us something about how we move to the right, right? It says
okay.
the slope
That's why
says
let me know, 'cause I'm also 5'3".
move right, do something, right? Go up or go down, right?
Yes.
If we want to know what happens if we move left,
But when you think about it, the rest of the clock is like
to move left,
really low.
simply reverse that. So for our case, where did we start? We started at -3. The slope said it's -2, so the slope says if we move to the right, go down 2. The way we want to understand how we move to the left on the line, then, is that if I move to the left 1, I should do the opposite. So instead of going down 2, I'm going to go up 2. Does that make sense?
Yeah.
They
that's how we
want to
can
stick with MailChimp and
learn that one.
we're
Okay.
trying to
So let's do another example here.
email address validation thing Salesforce, which there is an app and the app does work because I put in fake emails and it recognizes it. But I don't know how to pull a report from the app so we can upload that list to MailChimp or whatever.
Okay, so let me copy this. Or here, I'll leave this.
And I couldn't find any article on their support site, but there, I think
Just don't want
one of their
to lose my perfect graph thing here. So this was starting at -3 and going down 2/1, up 2/1, and then it looks something like this. Okay. So the next up, let's try another one. Let's try doing y is equal to 1/2 x plus 1. Let's try graphing this one. Well, what's my slope?
1/2.
And that's my rise over my run. Okay, rise over run.
Okay.
What about my y-intercept?
You'll have a point at 0,1.
0,1. Very good. That's the easiest part to get, isn't it? Just the y-intercept, because all you have to do is just go up to the point, to the value, right?
Yeah.
Okay, so we go through 0,1. Now the rise over the run slope says up 1 over 2. Right?
Yes.
So that's it. That's, I mean, oh, hang on, my iPad's not responding. There we go. So we want to go up 1 over 2, right? So let's just do that. That's the rise over the run. The run means how far left and right we go, and the rise means how far up and down we go. So it's a fraction in this form. It says that the rise should be 1 and the run should be 2. So how do I make that happen on the graph?
You go up 1 and then over to the right 2.
Okay, so that gives me a point right here, right?
Yes.
All right, now how do I go to the left?
Go down 1 and over to the left 2.
Yeah, exactly, right? Just reverse that process. So this one looks something like this. Okay. Shall we have one more example?
Sure.
Starting to lose my markings here. All right, let's do, I don't know, y equals, why don't I do this one? Y minus 3/2 x. No. Y minus, what if I do this? 2y minus 3x is equal to 4. How do I graph this one?
So wouldn't the slope then be -3?
Not quite. I haven't actually said anything, right, about how to graph a line when it's in this form, right? What do we know how to do? We know how to graph a line if it is in slope-intercept form.
Yes. So in that case, we would need to add 3x to add 3x to get 2y is equal to 3x plus 4, and then divide by 2.
And now this is a line that I know how to graph, right? We just learned how to graph lines that look like this.
Yes.
So if they give you a line which looks like this, don't get intimidated and think like, oh crap, I never learned how to graph lines when they look like that. Just make it look like one that you know how to graph.
Okay.
Okay, so now what does this graph look like?
That we have a point at 0, 2, and we'll go up 3 and over 2.
Very good. That looks like this. And then what if I go to the left?
We'll go down 3 and over 2.
Okay, so what point am I going to have on the left? Can you give me the coordinates?
1, 2, -1, -2.
-1, -2 is here. Because remember, this one is telling us the x coordinate.
Okay, just kidding. It's going to be -2, -1.
Yeah, -2, -1, right? -2, -1. This is 0, 2. And this one is 2, 5. Yeah. We have a line which goes through all of them. Great. Okay, so we've learned basically now how to graph lines and how to manipulate line equations when they're in standard form and slope-intercept form. There's one more form to cover, which is point-slope form. Paste again. I should just copy this and just never copy anything else. That'll work better. Okay, so point slope form is in sort of another category. Say I have something like y minus 1 is equal to 2 times x minus 3. Well, I could do this in a couple of ways. The first way to graph this equation would be to, well, just distribute out this 2. So I'd get y minus 1 is equal to 2x minus 6, and then add 1 to both sides. And then I'd have y is equal to 2x minus 5. And this is an equation which you know how to graph, right?
Okay.
Do you see what I mean by this process?
Yes.
So this is kind of just like what we just did with the standard form example, right?
Yeah.
Okay, so I can do that. And what would it look like? Well, it goes through -5, 0 comma -5, and it has slope 2, so we go up 2 over 1, right? Up 2 over 1, up 2 over 1, right? And it looks something like this, right?
Yes.
There's another way which we can graph this equation. This is in point slope form. And we said that an equation in point slope form goes through the point x naught comma y naught and has slope 2. So this equation goes through, remember, x naught here is going to be 3 because this is x minus x naught. And this is y minus y naught. The point goes through the point, goes through, the line goes through the point x naught comma y naught, which in our case is the point what comma what?
X no. -3, -1.
If y minus y naught is equal to y minus 1, then what should y naught be?
Hello?
1.
Yes.
Good morning.
Okay.
I am trying
So this is a
to
1 here, and then the x naught
you guys
should be what?
I
3.
Yeah, 3.
16.
So the number gets kind of switched in the sign.
Yeah, that
Minus.
lost me.
Yeah. Okay, so you're still confused about it, or you get it now?
No, like I just don't understand why it would not be negative numbers.
Okay, well, here's why it's true.
Okay.
If I have x minus x naught is equal to x minus 3, right? Which is what we have here, right? X minus x naught is equal to x minus 3. You can solve the equation in the following way. I can subtract x from both sides, right?
Yes.
And then I have negative x naught is equal to -3, right?
Yes.
And so then if I multiply both sides by -1, then on the left-hand side I get x naught, right?
Yes.
And on the right-hand side, what do I get?
3.
3.
Okay.
So in this place, the x naught is sort of taking the place of the 3.
Okay.
So if I have an equation where I have x minus something is equal to x minus 3, then the something has to be a 3 and not a negative 3. Because if I were to take x minus negative 3, that would be equal to x plus 3.
Okay.
Okay, so you can always go back and do that
Okay.
if you want to check it. Okay, so remember if we have x minus something, then the positive number will be here. And if we have y minus 1, then, well, y naught is the thing which is being subtracted. The thing which is being subtracted is the number 1.
Okay.
Okay, so what does this say? The slope intercept kind of method says, well, this is a line which goes through the point 3, 1 and has slope 3 or 2. So the other way to graph this equation is rather than graphing it like this, we just go straight to the point 3, 1, which is like right here.
Okay.
And then we just draw a line which has slope 2. So moving to the right, we should go over 1, up 2, and then moving to the left, we should go left 1, down 2.
Okay, sounds good. Thank you.
You see what I mean?
Yes.
So rather than starting on the y-axis, we start at a point which is somewhere else, you know, and then we just do our usual slope business from there.
Okay.
Okay, let's try another one. Let's try y plus 1 equals 3 times x minus 1. Actually, why don't I make it 1/3 times x minus 1. And let's try to graph this using the point slope method as opposed to the rearrange method.
Okay.
Okay, so how should I graph this?
We should it will go through the point 1, -1.
Very good.
And has a slope of 1/3.
Okay, great. So where's the point 1, -1? Which quadrant is it in? 1, 2, or 3, or 4?
4.
Good. We move over to the right 1 and down 1, right? That's that
Yeah.
xy. Okay, so we start at the point 1, -1. And then what does the slope do?
We will go up 1 over 3, over to the right 3.
Okay, good. Up 1 and over to the right 3. And what about if I go to the left?
You go.
Oh, I should have gone one more. Sorry. Up 1 and over 3.
Okay. Yeah. Then we will go down 1 and to the left 3.
Good. So down 1 and 1, 2, 3. Put this over here. Okay, so we have a line which goes through all these points like this. Okay. And this kind of shows us, actually, this example shows us why the slope-intercept form is sometimes a little bit more convenient than just always changing things into slope-intercept. Point-slope form, sorry. It's more convenient in this case, because if we wanted to do the slope-intercept method, well, we'd have to distribute that 1/3, right? And we'd get something like, we'd get, you know, y plus 1 equals 1/3 x plus 1/3, or minus 1/3, sorry. Minus 1/3. and then we'd add one, subtract 1 over to the other side, we get y is equal to 1/3 x minus 4/3, right? Because 1 is just 3/3. So if I take negative 1/3 minus 3/3, I would get negative 4/3. And see, this is not as good because the point is 0, negative 4/3 is hard to draw. Okay, because that's the point right here, 0, negative 4/3. And what's really easy is if we have a coordinate plane, we're good at drawing the points which are exactly at at a tick mark,
Yes.
You see what I mean? And drawing something like 0, negative 4/3 is kind of annoying. And then figuring out which points it passes through is even more annoying. But if I use the point slope method, I don't have to do any graphing of any points with weird coordinates. I just have to graph this point. 1, negative 1 is really easy to get my hands on. And then going from that point and going up 1 over 3 is no problem. Right? Whereas if I start at the purple point and I want to go up 1 and over 3, then I'm like, okay, so I go from negative 4/3 up to 1/3, and I go over 3, and then this is the point like 3, negative 1/3, and you get all these silly points with like annoying fractions,
Mm-hmm.
So this is the advantage of using point slope.
Okay.
Point slope is easier than converting to slope intercept in this case. Okay.
Okay.
Now let's do another example, and this one's going to be a bit harder, okay?
Okay.
But I'll be with you through it the whole time, so I'll try to make it not quite so hard. Okay. Let's do this one. Find the equation of the line which passes through the points 1, 1 and 2, 3. So the equation of this line, which passes through the points 1, 1 and 2, 3. Okay, so let's plot those 2 points, right? 1, 1 looks like, right here, and then 2, 3 is like up here, right?
Yes.
And we're supposed to find out what is the equation of this line. What is the equation of this line? So how can I find out the equation of this line? I have 2 points which it passes through. So, point slope maybe is an option because I have a point, right? So all I would need beyond that is, well, the slope of the line, and then I could use point slope.
Yeah.
That would be one method. So is there a way I can find out the slope of this line?
Couldn't you do like y2 minus y1 over x2 minus x1?
Yeah, definitely. Slope equals, usually we use y1 minus y0 over x1 minus x0. But if you want to use 2 and 1, that's also fine.
Okay.
We'll use 2 and 1. y2 minus y1 over x2 minus x1. So what is y1 minus y2?
3 minus 1.
3 minus 1. And how about x2 minus x1?
2 minus 1.
2 minus 1. So what's the slope?
2 over 1.
2 over 1. Great. Now, there's two methods which I can use from here. I have a point which it passes through. I have 2 points, in fact, which it passes through. And I have the slope. So I can use point slope right away. So let's try it. Point slope. We want y minus y naught is equal to m times x minus x naught.
Okay.
Now, what should x naught and y naught be?
Could we use 1 and 1?
Yeah. So how should my new equation look if I make this with all my proper numbers?
So y minus 1 is equal to 2 times x minus 1.
Yeah. And done. Not so bad.
No.
Okay, and then there's the other way we could do it would be to try to use slope-intercept, which would be to use the following method. We know the slope is 2 over 1, right?
Yes.
So if I start at the point 1, 1, and I move to the left 1, where should I go in terms of up and down?
Down 2.
So if I move left 1 and down 2, that puts me at this point right here, right? Which is the point 0,
Negative 1.
negative 1. And now I have the y-intercept, right? This is the y-intercept. So I could also do this using slope-intercept in the following way. I could just say y is equal to mx plus b, where what's my m?
1/2. Just kidding, no 2.
2, right? It's the slope. And then x is just x, and then what's b?
Negative 1.
So 2x plus negative 1, or in other words, just 2x minus 1. Okay.
Okay.
By the way, these two things are equal. Oops. Oh, come on. This thing is actually equal to this thing.
Okay.
To see why, we can just distribute that 2x, that 2 onto the x minus 1. We'd get y minus 1 equals 2 times x minus 2 times negative 1 is 2, right? And then we would add 1 to both sides. And we'd get y is equal to 2x. Negative 2 plus 1 is negative 1 minus 1.
Okay.
So these two equations are really the exact same thing. They're just written in a slightly different way.
Yeah.
For example, we could write the equation 6 plus 1 equals 6 plus 1, or we could write the equation 7 is equal to 7, and they both mean the same thing, right?
Yes.
So that's kind of the situation with point slope and slope intercept, is they are both different ways of expressing the same line.
Okay.
Okay, let's see if I can come up with something even more dastardly than I've already done.
Okay.
Let's see, we talked about slope, intercept, and all right, let's try something like this. Maybe I can throw you off. Actually, I doubt I can throw you off with this, but we'll see. Let's try 2y minus 3 is equal to, no, 2y minus 3 plus x is equal to 2x minus 2.
Okay, 2y. Okay. So, first I would subtract x from both sides.
Dang, you saw right through my trick. All right, now what?
X minus 2. And then I'd add 3 to both sides.
Equals x plus 1, right?
Yes.
All right.
And then divide by 2.
Okay, so then y is equal to 1/2 x plus 1/2. So now how do I graph this?
So we have a point at 0, 1/2. And for every time we go up 1, we move over 2.
Okay. So there's another way we can think of this, by the way.
Okay.
If the slope is 1/2, we can think of this in 2 ways. We can think up 1 over 2, or we can think of it as 1/2 divided by 1, in which case we would say up 1/2 over 1. Does that make sense?
Yes.
That's another way we can think about it. So if we start at 0, 1/2 and we go up 1/2 and over 1, then we'd be right squarely at the point 1, 1.
Okay.
Which, by the way, you could see from this equation, if we were to put it in slope-intercept, or point slope form, we could rewrite this equation in the following way. Y minus 0 is equal to 1/2 times x plus 1.
Okay.
If we rewrote it that way, then we would know that this... No, wait. Oh, yeah, this is right. And then from here, we could see that, well, x0, y0 would be the point, well, x0 would be -1, right? Because it's a plus in here. And then the y0 would just be 0, right?
Yes.
So then we would go to the point -1, 0. That's this point right here on the left, -1, 0. And we go up 1/2 over 1, or up 2, or up 1 over 2. Sheesh. I speak. Okay, so that's 2 different ways of thinking about it. You can always switch back and forth between these point slope things and the slope intercept.
Okay.
Okay. So the final thing on lines, I think, which I have to say is that 2 lines are perpendicular. 2 lines are parallel if they share the same slope. For example, y equals 2x minus 1 and y equals 2x plus 1. If we were to graph these, they would look like, well, 2x plus 1 is we go through the point 0, 1 and we go up 2 over 2, right? And we look something like this.
Mm-hmm.
Whereas 2x minus 1 looks like, well, same slope, but it goes through the point 0, -1. Is that clear?
Yes.
So the reason that they're parallel is, parallel, if you think about just like the word, what it means in real life, right, is like right next to, right? Parallel. If you're parallel parking, then your car is on the side of the road and it's facing in the same direction as all the other cars, right?
Yes.
So if you're parallel parking, that's kind of what that means. So these two lines are going to be going in the same direction, but they may not go through the same points. It's saying something about the direction which they're going in.
Okay.
The direction which the lines are going in is characterized by the slope.
Okay.
So two lines are parallel if they share the same slope.
Okay.
The last thing I have to say here would be that two lines are perpendicular if m2, the slope of the second line, is equal to -1 over m1. For example, y equals 2x and y equals -1/2 x are perpendicular. Oops, crap, I got rid of my stuff here. Okay, well, copy this, paste, get rid of my second line here. Actually, I gotta move the other one too. Why don't I make 2x? I'll go back to 2x plus 1. Doesn't matter what the y-intercept is, right?
Yeah.
And then I'll do -1/2 x plus 1 as well. I'll make them have the same y-intercept. They both go through this point 0, 1, except the slopes are different. The first slope is 2, right? Which means go up 2 over 1. The other slope is -1/2, which means go down 1 over 2. Okay, so go down 1 over 2. Okay. And what you'll see if you graph this is these two lines meet in a way such that they form a right angle.
Okay.
I don't know, maybe I can, where's the best place to put this right angle? Yeah, probably right there. Okay. So the slope of the new line should be the negative reciprocal. Okay, so the reciprocal of 2 is just 1/2, but the negative reciprocal is -1/2. Okay. If you ever have trouble remembering that this negative should be a part of this, it should be clear, right, that if we have two perpendicular lines and one of them is going up, the other one should be going down, right?
Yes.
So they should definitely have opposite sign. And then you just have to remember the reciprocal part beyond that.
Okay.
Okay. So that's, I think, all I have to say about lines for today. Do you feel better about this stuff now?
A lot better.
Okay, good. So, if we go back to what the actual problem was, I don't even remember what the problem was. I mean, we'd be able to solve it quite easily just based on what we just learned, right?
Yes.
So they said, find the equation of the line parallel to 2x plus 3y equals 4. So let me just recap what I did on this problem. Well, I took 2x plus 3y equals 4, and I did what seems to be kind of your preferred method, which is I took it here and I rearranged it until it was in slope-intercept form.
Good morning.
Right?
Yes.
Once I had it in slope-intercept form, I said, well, I need to find another line, line 2. It should be parallel to this line, so its slope should be the same. So the slope should be -2/3.
Okay.
And it was also supposed to pass through the point -3, 0.
I
So what I wound up doing was I just used, well, I could have used slope, point slope form, right? Which would be, you know, y minus y naught equals m times x minus x naught. And we know that this point here is x naught comma y naught, right?
Yes.
And we know that the slope is negative 2/3. So if we plugged in, we'd get y minus, well, y naught is 0 is equal to, the slope should be negative 2/3 times x minus, x naught is negative 3, so x minus negative 3 becomes x plus 3. That's it.
Okay.
630. Yeah.
Okay.
Okay.
The way that Justin wanted to solve the problem was slightly different. He said, well, we know that the slope should be negative 2/3, so I know that the equation should have the form y equals negative 2/3 x plus b if it's in slope-intercept form. And then he said, well, since this is a point which is on the graph of the equation, we can just go ahead and plug it right in. So we put the 0 where the y goes, we put the negative 3 where the x goes, and we solved for b.
Okay.
So that's just a slightly different way of doing the problem.
Okay.
All right. That's good. Because I don't know if like I will need
Okay,
this
so
late and I don't want to keep you at work.
next time we'll do the perpendicular line in class, and then we'll carry on with this problem. But hopefully you feel better about lines now.
Yeah.
Any further questions before we close?
Just one. So when we did find the equation of which passes through points 1 and 1 and 2 and 3, could I have used so I decided to use negative 1 and 1, I think. Could I have used the 2 and 3 as well?
Definitely.
Okay.
Yeah, so we got this equation. There's another equation which is equal to all of these, which would be the point y minus 3 is equal to 2 times x minus 2.
Okay.
Yep. These things are the same again, because again, if I distribute, I get y minus 3. Y minus 3 is equal to 2x minus 4, right? And if I move the 3 over, I'd get y is equal to 2x minus 1, which is again the same as this.
Okay.
Yeah. Okay.
So 3 ways of writing the same line.
All right. Now we'll
Perfect.
go make sure.
Yeah,
I
as
know
long as you
all
have
the tips that you
the
give me.
slope, which will be unique, and a point which it goes through. It doesn't need to be a specific point. It can be any of the points. If you use the point which is on the y-axis, then you exactly get the slope-intercept form.
Okay.
Yeah, that's a good question.
All right. Sounds good. I will.
All right.
Thank
More
you.
questions?
Have a good day.
That was my only one.
Okay. All right. Well, we'll continue tomorrow, and then if you want to ask more questions about other topics, I'll have office hours again on Wednesday.
Okay, and I am planning to do MTC this
Okay, yeah.
week. Start that. When you don't have office hours, I will go there.
Yeah, that's a really good idea.
Okay. All right.
Alrighty. Cool. All right. Well, then, final question. Do you mind if all this stuff that we talked about on office hours, can I put it on the YouTube channel?
Yeah, absolutely.
Okay. I think other students would I think, benefit from this review. So,
Yeah.
okay, cool. Stop recording and